Okay, so what we want to do now is introduce a method for a numerical method for approximating a solution to a first order DE. It does the same thing that Euler's method does, but it's going to give us more accurate results. And it uses Euler's method as a starting point and just improves it. So for that reason, we're going to call this the improved Euler's method. This goes by other names as well. You know, if you were to look this up somewhere else, you might see it called the modified Euler's method or Heun's method. I'm not actually sure if I'm pronouncing that right. It's H-E-U-N. It has other names as well, but we're going to be calling it the improved Euler's method. So the way the improved Euler's method works is you actually start on the second line right here, and notice the recursive formula that's being used here is Euler's method. Okay, so if I want to evaluate y n plus 1 star, then I'm gonna plug xn into this formula. Okay, and what this does, like we saw before when we talked about Euler's method, is it's computing a tangent line to the point xn y of xn, which would be an actual point on the curve, the solution curve itself. But if yn is not exactly equal to y of xn, then it'll become a line that's parallel to that tangent line. And that's supposed to kind of give us the general direction that the curve is moving at that point. Now, looking at this graph down here, here's where we're starting, x naught, y naught. That's an actual point on the curve itself. So using Euler's method produces a tangent line, and then once we get to x1, which we find by adding our step size to x naught, we would plug that back into our recursive formula to get an approximation for y1. And notice here we're calling that y1 star. Okay, so the next point that we get from our recursive formula would be a point that lies on this first tangent line. Now notice that's off, right? There's error there because the curve itself is concave up. It's curving upwards and away from that tangent line. So the actual value of yx1, which we're trying to approximate, is way up here. Okay, so in this particular graph, it looks like there's a fairly large error right away. That's what we would call that local truncation error. Now, what the improved Euler's method does is once we've evaluated this point, this y1 star, we compute a second line that passes through this same point, but it's no longer a tangent line. It's technically a secant line. And where do we get that from? Well, it comes from, we're going to be using this formula up here, f of xn yn. Now remember, this is what y prime is equal to. This function represents slope. But then we use that function f again. We use it with xn plus 1, which would be the next x value, in this case x1 in our sequence of x values, and then we use that yn plus 1, I should say plus 1, right? Or yeah, it should say n plus 1 right there. I think that's a typo from the book. Star. So we're using the approximation given in this previous step here. And essentially what that does is it's attempting to find a tangent line using this point, y1 star, at least in this first step. Okay, so notice we have two lines that have been computed, or at least two slopes that would have been computed using these two values. Then we divide it by 2. And what that's doing is it's averaging these two slopes. So here's the basic idea. At this point, at least for this particular solution curve, our slope is too shallow because the curve is increasing in its slope. It's concave up and increasing away from our tangent line here. This second slope that we've computed, because we've used a point that comes later on down the line, is going to be steeper. So we take this slope that's too shallow, we take this second slope that's steep, and we average the two, and notice what happens. The average slope between these two would be the slope on this red dashed line. Now, the rest of this recursive formula would put that line through this initial point right here. And if you follow that red line, once you get to x1 here, you can see that the point is significantly closer than to the true value that we're trying to approximate than Euler's method gave us. Okay, so by averaging those two slopes, we get the improved Euler's method, and it'll do that every step of the way. Now, this is a type of method. There's several other methods like this one that we call a predictor corrector method. So that implies two steps, which we have here. Euler's method is the predictor step. So what Euler's method does is it makes a prediction as to where y of x1 would be, and it calls it y1, or in this case, y1 star. Then it recognizes that there is a local truncation error, and it attempts to correct that error using this second formula. Averaging the slopes and then plugging that into plugging that new averaged slope in as the slope for Euler's method produces a correction. Now, it's not a perfect correction, but it does improve that local truncation error. So that's where we get that name. Okay. Now we could analyze this in the same way using Taylor's theorem to try and find the order of that local truncation error term. And it turns out that the improved Euler's method has an order of h cubed. Remember, Euler's method by itself had an error that was on the order of h squared. And we said that the higher that exponent is, the better the algorithm, because it's producing producing more accurate results. So that we're not going through the error analysis right now, but we could, and we would arrive at this result. This is showing that the improved Euler's method does in fact have a generally better error term than Euler's method by itself. Okay? So we're going to go through an example here. And I'm going to show you what some of the computations look like for Euler's method, but I've given the answer in the form of a table here, so we're going to reference the table. Our goal here is to use the improved Euler's method to find a 4-decimal approximation to y of 0.5, where y is the solution to this differential, or this IVP. Y prime equals x plus y squared. Y of 0 equals 0. And we're going to use a step size of h equals 0.1. Okay? So this table, this printed kind of faint, but this is xn, and this is the approximation. So really this, I can call this xn and yn. Okay? And our initial value is going to fill out the first two, the first row of this table, 0, 0. Okay? Now, again, Euler's method has two steps. So, the improved Euler's method in each iteration. First, I need to find this yn plus 1 star thing, which looks like the normal Euler's method. So, we have y0 already. What I want is y1 star. y1 star is going to be equal to y0, which is 0, plus our step size of 0.1 times f of xn yn. Well, remember, that's this function right here. F of xn yn is f of 0, 0. That's 0 plus 0 squared, which in this case turns out to just equal 0. The next thing I need to do is take that y1 star and feed that into this recursive formula showing up here. Here's where it gets entered in. Okay, so let me actually do this so we can have the formulas handy so you can see them. Okay, so what I'm going to do is find y1 by entering the information that I need into this formula. y0 would show up here, again, that's 0, plus h, our step size of 0.1. Now here we get this big rational expression. So f of xn yn. Remember, we evaluated that here. That was 0 plus 0 squared. Plus xn plus 1 y star of n plus 1. That's, in our case here, that would be xn y1, or sorry, x1 y1 star. x1 comes from adding our step size to x0, which would be 0.1. plus y1 star, which is 0 squared, because remember that's what the function looks like. Okay, this is equal to 0.005, which is where this is coming from in our table. Okay, now what I would do, I would take this result and feed that back in to our formula. So now what I want is y2 star. And that's going to be equal to y1, which we have here, 0.005, plus my step size of 0.1, times f of x1, y1. So x1 is 0.1, y1 is what we found here, and the formula squares that. It's up there, right? So plus 0.005 squared. And this is equal to 0.0150025. Okay, it's a 1 right there. This gets fed back into that second formula. So y2 star is going to equal y1, which was 0.005, plus my step size of 0.1, times this big rational expression here. This is going to look like f of x1, y1, that's 0.1, plus 0.005 squared, plus f of x2, which is 0.2, y2 star, which we just found here, squared, 0.0150025 squared. Okay, that comes out to a value that's that's approximately 0.02001. This table rounded it to just 0.2, but you would continue this until you eventually get to this entry in the table. Okay, and that's going to be our answer. So notice again, it's similar to Euler's method, the way that we start, but Euler's method gives us this starred value. That's the predictor, right? So we get the predictor, we feed that back into the other formula, which is the corrector, and we get an improved estimate for that y1 in this case, or y2, or whatever step in the table you're in. Okay, so that is the improved Euler's method. We're really just doing one example because all the other examples would be essentially the same, just with a different f of x, y. In the next section, 9.2, we're going to see that both Euler's method and the improved Euler's method are both special cases of a much more general family of numerical methods. And we'll look at that family of numerical methods and derive one that's even better than these. Well, I say derive, we're not going to go through a full derivation. It's extremely, extremely messy to do the full derivation. But we're going to talk about where it comes from. And we'll derive a method that's significantly better, so much so that it's one that's kind of one of the standard algorithms that's actually used in practice. But that's going to be it for 9.1.